Good evening, everyone. It is Mr. Spaghetti. This is my second time attempting to record this, so forgive me if I sound impatient. The first thing we're going to look at is the definition of the derivative. On the left, we have the one you're probably more familiar with. That's the limit as h goes to 0 of f of x plus h minus f of x all over h. And if we look at this common problem type below, you'll see an ugly mess, but you'll notice x plus h's. Now, if you carefully distribute the negative through to all of these, you will see that that is your original function, but you have to be careful to change that to a minus, this to a plus, and this to a plus. So I think it's easier to look at the original with all the x plus h's, replace those with x's, and you see that your original function that you are attempting to take the derivative of is 2x cubed minus 7x squared plus 3x plus 2. So we're going to apply the power rule to this, and we get 2 times 3 is 6. Drop the power down 1 is 2. Minus 7 times 2 is 14. Drop the power down 1 is x. The derivative of 3x is 3, and the derivative of the constant 2 is 0. So another problem we might see is one like the one at the bottom, which ties back to the other definition of the derivative, which is as x goes to a, of f of x minus f of a all over x minus a. Now we can see in this particular problem we actually have a value of a, and we can very readily see what we're taking the derivative of. So we are computing the derivative of the negative cosine of x, and we are going to evaluate that, you'll see me use that bar a lot this year, at x equals pi over 6. So no longer are we just doing it at some random point a, we have a specific point. Now the derivative of negative cosine of x is negative sine of x, so the negatives cancel out, and we end up just getting the sine of x evaluated at pi over 6, which is a positive 1/2. So knowing these definitions of the derivatives, we can make these ugly problems very easy by converting them to the equivalent derivative form. Now the next thing we look at is graphing our derivative given a function. So what I'm going to focus on first is where these functions have horizontal tangencies. That's going to happen at the peaks and valleys, or places where nothing changes. So I'm going to plot those points on my derivative as being values of 0. So at x equals negative 3, at x equals negative 1, and at x equals 2, I have zeros. Now I want to see where my function is increasing and where my function is decreasing. So I'm going to focus on the increasing first. My function f of x is increasing here, here, and here. So what does that mean? It means the derivative is positive. So when I graph my derivative on those intervals, I need to be above the x-axis. So I'm above the x-axis here, and I'm above the x-axis from, I erased one of my zeros, and I'm above the x-axis here. I bounce at 2. My derivative went from increasing to 0 to increasing, so I must bounce there. That's my dog Gratch having a great time playing all by himself because his older brother is tired. Now when I look at the other part of the function f of x, where it is decreasing less than 0, so again f prime of x is less than 0, that means on my derivative I need to be below the x-axis. Doesn't quite matter what it exactly looks like, but if you're curious, the original looks like it was changed directions 1, 2, kind of 3, 4 times, and you can see that my derivative, so this was probably an x to the 5th up here, and this was an x to the 4th down here. So you can also keep that in mind and how your derivative will look. Over here, I'm going to do the same thing, determine where my function has a horizontal tangency, and that appears to be at -1, 0, and 1. So I'm going to go to my derivative, plot those points, -1, 0, and 1. Then I'm going to look at where this function is increasing. The function f of x is increasing from here to here. So I need to be above the x-axis and bounce at 1. So I'm above the x-axis, bounce at 1, but I'm still above the x-axis because my function f of x was increasing. Now I look at where my function is f of x is decreasing. Where that function is decreasing, f of x, my derivative, f prime of x, should be below the x-axis. And I bounce at the point x equals -1. So again, wherever my function f of x was decreasing, my derivative is less than 0, so below the x-axis. Wherever my function f of x is increasing, my derivative f prime of x is above the x-axis. Hope I didn't just say the wrong thing. F prime of x greater than 0, increasing. F prime of x less than 0, decreasing. Now, this problem is just an ugly mess, but it shows very common things that occur on derivative problems. So the first thing I'm going to do is rewrite this problem in a way that I can apply the power rule and the derivative of sine and cosine. So I'm going to rewrite this as f of x equals. This first part I'm going to rewrite using some basic algebra. So 3 divided by 3 is 1. X to the 2 over x to the 4 is 2 minus 4, -2. -9 over the 3 gives me -3. X over x to the 4th is 1 minus 4, which is -3. And then I get plus 4/3 x to the -4th. So all I've done is rewrite that in a way that is convenient for me to apply the power rule. I go to the next term, and this is really x to the 2/3 minus x to the 3/2. Sorry, x to the 2/3 minus 3/2, which I will simplify as converting it to 6, 4/6 minus 9/6, which gives me -5/6. That part in blue is really x to the -5/6. Then I proceed to the last part. I don't need to bother rewriting that. It is nothing exciting. Now I go through, apply the power and chain rules, and power rule and derivative of trig functions. You don't know chain rule yet. And I get -2x to the -3rd plus 9x to the -4th minus 16/3 x to the -5th minus 5/6 x to the -11/6 plus 2 cosine of x plus 8 sine of x, because the derivative of a negative cosine would be a positive sine. The negatives multiply to make a positive. So that would be my derivative. I could and should rewrite it, and I shall. I get f prime of x is -2 over x cubed plus 9 over x to the 4th minus 16 over 3 times x to the 5th minus 5 over 6 times x to the 11/6 plus 2 cosine of x plus 8 sine of x. And I should have written this portion here. I will do that in blue. It should have been 6th root of x to the 11th in the numerator. So that is a little side note. Could have also written it like that, and I should have if I apply my rule of no rational exponents. So again, what did I do? The part in red I rewrote as 3 separate fractions so it would be in a form suitable for the power rule. I did the same for the part in blue, and the trig functions I just had to remember the derivative of sine is a positive cosine and the derivative of cosine is a negative sine. Now the next thing we encountered in Unit 2 was intervals of increasing and decreasing, and our extrema, where do we have maxes and mins. Key thing we're going to do here, take the derivative, set it equal to 0. We're going to do that so much in this class. That gives us so-called critical numbers. Then we create a sign chart, and we use the factored form of our derivative to determine to the left and right of those critical numbers if we have positive values, which is where we are increasing, or if we have negative values for our derivative, which is where the function would be decreasing. Then it goes without saying that a max occurs where you go from increasing to decreasing. A min occurs where you go from decreasing to increasing. Again, we will reference the derivative when we talk about all of these things. What does a sample problem look like? Well, here's a very basic one. Here's a function, find where it's increasing, decreasing, and compute the extrema. So the first thing I'm going to do is take my derivative. I take my derivative, I get 12x cubed minus 12x squared. That isn't the best, so I'm going to factor it. Factor out a 12x squared, that leaves me with x minus 1. This is my factored form. It is my friend. I'm going to set that equal to 0. Which means if I look at these two parts, this first part gives me x equals 0. Note the multiplicity of 2 is an even number. That'll be interesting to see how that affects my derivative. And the x minus 1 equal to 0 gives me 1. So I create a sign chart with my two critical numbers, 0 and 1. I plug numbers to the left and right of those. Doesn't matter what I plug into the 12x squared part, it will always be positive. So really I want to see if numbers to the left and right of 0 and 1, when I subtract 1, give me positive or negative. So to the left of 0, negative a billion, minus 1, negative. In between 0 and 1, how about a half? 1 half minus 1 is negative. Plug in a number bigger than 1, subtract 1, it's going to be positive. So what does my function look like? It is going down, down, and then finally going back up. So I would say that it is increasing on the intervals 1 to infinity, because the derivative, so I'm going to little shorthand, because f prime of x is greater than 0, it is decreasing negative infinity to 0 union 0 to 1, because f prime of x is less than 0. And finally, I can determine where I have a max or min, and that is only a min. I have a min at x equals 1 of, plug 1 into the original function f of x, of f of 1 equals 3 minus 4 is negative 1. So notice that at 0, nothing exciting happened because it kept decreasing. It went from decreasing to a horizontal tangent to decreasing. Now the next problem is a fun one. It gives me the derivative. Well, if you remember my steps, I need to set the derivative equal to 0. Well, that's pretty easy to do because it was nice and gave it to me in factored form. And I see from the first term, 2x squared, I set that equal to 0. I get 0. Again, note the multiplicity. I forgot to discuss that here, but the even multiplicity at 0 meant that it stayed decreasing. Went decreasing to decreasing, it did not change. Let's see if the same thing happens down here. Now the x plus 4 set equal to 0 gives me a negative 4. The x minus 3 set equal to 0 gives me a positive 3. So I'm going to plug values into my derivative. To the left of negative 4, anything I square is going to be positive, so I'm just looking at x plus 4 and x minus 3. Well, plug in negative a billion, add 4, it's negative, subtract 3, it's negative, negative times a negative is a positive. Plug in negative 2, add 4 is positive, subtract 3 is negative, positive times a negative is a negative. Plug in 1, 1 plus 4 is positive, 1 minus 3 is negative, positive times a negative is a negative. So again, at 0, the sign of the derivative did not change due to that multiplicity that was even. Plug in a number bigger than 3, you'll find that the derivative is positive. So where is this thing going up? F of x is increasing from negative infinity to negative 4, union 3 to infinity. Where is the function decreasing? Well, it's decreasing wherever my derivative is negative. So f of x is decreasing from negative 4 to 0 and 0 to 3. Then the last thing I'm going to look at is where do I have maxes or mins. Got a max at x equals negative 4, and I've got a min at x equals 3. Why do I have a max at x equals negative 4? Because f prime of x goes from increasing positive to decreasing. Why do I have a min? Because it goes from decreasing to increasing. Okay, so that would be a reason you would give. I would say it's increasing because the derivative was greater than 0. And I would say it's decreasing because the derivative is less than 0. So increasing, decreasing, I look at if the derivative is positive or negative. Maxes and mins, I make sure that the sign of the derivative is changing appropriately. Now the last thing we talked about were tangent line approximations. To write the equation of a linear equation, I need a point and a slope. I get the point using the original equation, and I get a slope by using the derivative. So common problem types, you may see a table. So this one, blah, 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 blah. I look at the first question. It says, if f of negative 1 is 4, find the equation of the normal line at x equals negative 1. So I look at negative 1, and I see the derivative is negative 1, which means that the normal line is going to be the negative reciprocal of negative 1, which is just a positive 1. So that will be my slope. It gave me a point of negative 1 comma 4. So I write my equation of the normal line using point slope form. Y minus 4 equals a positive 1, which I will actually write because it helps us in the next problem. And I do an x minus a negative 1, which is x plus 1. So again, normal line, I needed the negative reciprocal of that derivative. Then I apply point slope formula. For the second problem, it says find the equation of the tangent line and use that to find an approximation at a point. So I'm going to use the same exact equation I wrote above, except instead of 1 for my slope, I'm going to use the negative 1 that I got from the table because I'm going to use the tangent line, not the normal line, to approximate the value. So, in order to compute this approximation, I need to plug negative 0.9 into my tangent line approximation. So, I get that it's approximately negative 1 times negative 0.9 plus 1. Add the 4 from the left side. I see that on the inside of this, I will get a positive 1/10. So I end up with negative 1/10 plus 4, which is equal to 39/10 or 3.9. If you had the original function, you could compare it, and because -1, where I computed the tangent line, and the x value -0.9, because -0.9 and -1 are not that far apart, my approximation should be pretty good. Now the next question asks where the function is increasing and decreasing. I'm going to make my life easy and make a sign chart. So I notice that at -2, 0, and 4, my derivative is equal to 0. So -2, 0, and 4, I want to see where is this function decreasing and increasing. So I'm going to look at the positive and negative nature of my derivative. So to the left of -2, f prime is negative. In between -2 and 0, it's negative. In between 0 and 4, it's positive. And then to the right, it's negative. So where is my function increasing? It's increasing on 0 to 4. And it's decreasing from -infinity to -2 union -2 to 0 union 4 to infinity. Where do I have a max and a min? Well, as you know, I like to graph where my function is actually going down and where it is going up, so that I can very easily see where my maxes and mins occur. So I can see I've got a min at x equals 0, because it goes from decreasing to increasing. It being very specific, because f prime of x goes from negative to positive. Therefore, f of x goes increasing. Oops. Ooh. Goes from increasing to decreasing. I have a max at x equals 4, because the derivative goes from positive to negative, which means my original function, f of x, goes increasing to decreasing, which obviously, if you are still awake at this point, you realize that I made a mistake at the top, and I should have said it goes from decreasing, the function f of x, to increasing. Okay? So again, we use the sign chart to determine where the derivative changed signs. That determines where we have mins and maxes. Now the other type of tangent line approximations you might see, this is not a tangent line approximation, this is more of a increasing, decreasing type question. So, in this first problem it says, when is the function f of x increasing and decreasing? Well, it's decreasing from here to here and here to here, simply because the slope is negative. Derivative is less than 0. That's almost like a pre-calc question. And then it's increasing, it's going up because the derivative is greater than 0. Kind of a boring question, but it's easy to get tripped up because the very next question asks about g of x, but the graph is g prime of x. So we focus more on where is the function g prime of x above the x-axis, which I've highlighted in green. Those are places where it is increasing. So it is increasing from -infinity to -2, and from 2 to infinity. Then I focus on where the function g prime of x is below the x-axis. So because the g prime of x, the derivative, is less than 0, then g of x is decreasing. That takes place on the intervals -2 to 0 and 0 to 2. So again, you got to pay close attention to if you are given the derivative or the original function. So that's all I've got for Unit 2. Hope you enjoyed. Let me know if you've got questions.